Good morning, sir. Yes, we are learning physics today. I am going to wait until there are more than 20 people, let's say 23 people watching, and then I will begin the class. Salutations. Greetings. We're waiting to have at least above 20 concurrent viewers, and then I will begin my lesson. You are enough for me. The 13 of you are enough for me, but you know, I'm still going to wait. Whoop, the concurrent viewers went down. Good morning, Spicy Pepper. I have no clue what that means. I smell cap. I hope you guys had an enjoyable wolf den yesterday. I had a pretty interesting wolf den. I have some interesting students in there. I have a student who was a Ukrainian, or who is a Ukrainian citizen, and he said that over the summer he toured, or he went to a nuclear launch facility, a former Soviet nuclear launch facility, and I guess it was like abandoned and you can just sort of walk in. And I was like, well, gee, aren't you worried about radiation? And he was like, oh, it's always a good idea to have a Geiger counter when you're in the Ukraine. So he had a Geiger counter and was walking around. Because, Chernobyl happened in Ukraine. Oh man, these people are slow to join. Come on, people. You know what? Forget it. I'm just going to start. First thing I wanted to talk about is I wanted to remind you to submit your daily attendance for today if you haven't already. The second thing I wanted to talk about is I wanted to remind you that your first quiz is due tomorrow at 11:59 p.m. So whatever work I assign you is always going to be due on Friday of the following week. Okay? Hello, Josh. So for example, the work that I assign you today is going to be due next week on Friday. Okay? So I'm going to go ahead and get started. Do you have to do daily attendance twice if you have 2 of my classes? Yes, because it's checking your attendance based on when you submitted the form. So if you didn't submit the form during the at the right time, it's not going to register your attendance for that class period. Okay. So I'm going to start off with just a really brief review of how to take a derivative. okay? Because this is a calculus-based class, and I know that some of you are might be concurrently taking calculus, so you are learning calculus for the first time as we speak. And so I'm going to teach you what you need to know to get through today's lesson. It's really simple, okay? So let me show you. Here's what we're going to learn about first, is how to take the derivative of a polynomial, okay? So let's say we have a polynomial, like maybe 5t cubed, okay? And we're going to take the derivative. So when you take the derivative, you write d dt. That's the derivative with respect to time. Okay. And what you want to do is you want to bring the power down and you want to multiply the expression. So we're going to ignore the factor of 5 that's in front. All that we care about is the power of t. We're going to bring that power to the front. So we're going to write 3 in front. And we're going to keep the 5. And then when we write t again, we're going to reduce the power by 1. Okay? So that would be 2. All right? So when I take the derivative of 5t cubed, that is going to be 15t squared. That is how you take the derivative, okay? What if I have a sum of two terms? Okay, so what if I had negative 4t to the 9th minus, let's say plus 3t. And I want to take the derivative of that. So if you have two things added together, you what you want to do, okay, is you want to take the derivative of the first one and take the derivative of the second one and add them together, okay? So taking the derivative of the first one, I'm going to bring down that power. So I have 9 times negative 4. And then I'm going to reduce the power by 1. So that would be 8. Okay? And then I'm going to add that to the derivative of the second one. Now, if I don't explicitly put the power of t, that means that the power of t was 1. Okay? So I'm going to bring down that 1. So I have 1 times 3. And then I'm going to reduce the power of t by 1. So I have t to the 0 power. Now anything to the 0 power is just 1. So when I get my final answer, I have minus 36 t to the 8th plus 3. Okay? So that is how you take a derivative, and every year I teach this class, there's always like 4 or 5 of you who are currently taking calculus for the first time. So I always like to include that. Okay, we're gonna be using this today. All right. So the first thing I want to talk about is the position vector. Which I will denote by r. Okay? And the position vector extends from the origin, so there's the origin, to wherever the particle is. So maybe this is the path of the particle, and at a particular moment, the particle is right here. So the vector that extends from the origin to wherever the particle is called the position vector. Okay? Maybe this is where the particle is at time 0. Okay? And maybe the particle's moving around. So maybe here is the position of the particle, at time 1. So there's the new position vector. So this would be r of 0. Okay. This would be r of 1. All right, and maybe at time 2 it's over here. So this is the position of, this would be r of 2, etc. Okay? So our position vector, r of t. Now notice how the horizontal component is how far to the right of the origin it is. So that is the x component. So we have x of t times I hat. And then the y component of this vector is how far above the origin it is. So we have plus y of t times j. All right, so that is the position vector. Who can tell me, type it into the live chat if you know, what would this mean? And I'll wait a second while I do that. All right, so while I'm waiting for someone to type that in, we will talk about the velocity vector. Okay. The velocity vector, which is denoted by v. And, okay, someone typed in the distance from the origin of the particle. Excellent, that is correct. So the magnitude of r of t is the distance from the origin. Okay. All right. So what is the velocity vector equal to? The velocity vector is equal to the derivative of the position vector. Okay? So you can actually take the derivative of a vector. How do you take the derivative of a vector? Well, just like when you take the derivative of a sum of 2 powers of t, you take the derivative of the first one and the derivative of the second one and you add them together. Similarly, when you take the derivative of a velocity vector, or of a position vector, you take the derivative of the x component, and then you take the derivative of the y component, okay? So it's going to be dx dt times I hat plus dy dt times j hat. Okay, so that is the position vector. All right, now how does the position vector point? Okay, if this was the actual path of the particle, okay, through two-dimensional space, the velocity vector is always going to point tangent to the path. So this would be the direction of the velocity vector at 0. Here would be the velocity vector at 1. Here would be the velocity vector at 2. So the direction of the velocity vector, direction equals direction of travel. Okay, and then if we were to take the magnitude of the velocity vector, we would get the speed. Okay, the magnitude of the velocity vector is your speed. Okay. So, and if you recall, the magnitude of a vector is equal to the length. So as I've drawn it right here, you can see that v of 2 is longer than v of 1. And so that would mean that the particle is going faster at 2. Okay. So that is the meaning of the velocity vector. And then we also have another vector called the acceleration vector, which is denoted by A. And that is the derivative of the velocity vector. Okay. And so again, we would take the derivative of the first term, and we would take the derivative of the second term. All right. So this is the acceleration vector. Now, if you are new to physics, this is your first physics class, which I know it is for some of you. The units of position are meters. So if I put square brackets around a variable, that means units of. The units of velocity are meters per second. And the units of acceleration are meters per second squared. Okay. So let's do an example to illustrate these concepts. And by the way, I want to say that these techniques, they extend in the obvious way to 3 dimensions, okay, and higher dimensions. Okay, so we got an example here. Let's suppose that the position vector, okay, is equal to, I don't know, let's say 2t cubed minus t times I hat plus 4t to the 4th times j hat, and that's measured in meters, so I'll put parentheses m behind it. Okay. So let's go through some of this stuff. What if I wanted to know how far? Well, you know what we'll do first. First, let's find the velocity vector. Okay. The velocity vector as a function of time is going to be take the derivative of the first component and take the derivative of the second component. So the derivative of the first component is 6t squared minus 1. And the derivative of the second component is 16t to the 3rd. Boom. So that's the velocity measured in meters per second. And then our acceleration vector is going to be the derivative of the velocity vector. So taking the derivative of 6t squared is going to give us 12t. And the derivative of a constant is 0. I forgot to say that in my rules over here. So if you have just a pure number, the derivative of a number with no factor of t multiplying it, so for example, the derivative of 5 is 0. Okay? So taking the derivative of this constant term is going to kill that term, and so that one just disappears. And then taking the derivative of the y component is going to give me 48t squared. And that would be measured in meters per second squared. All right? So I have my position vector, my velocity vector, my acceleration vector. Now let's ask some questions about that stuff. So what if I said, how far from the origin is it? At t equals 1 second. So what it's asking for in that case is the magnitude of the position vector evaluated at 1 second. Okay? So what I'm going to do is I'm going to type in 1 second for time. All right, so what does that give me? It's going to give me 2 minus 1, so that's just going to be I for the I component. And then if I plug in 1 here, that's going to be 4 times 1 to the 4th power, which is just 4. So plus 4j. And then to do the magnitude of a vector means to do the Pythagorean theorem. So I would use square root of 1 squared plus 4 squared. So that equals square root of 17 meters. And I would convert that to decimal. Okay? What if I asked, what is the speed at t equals 1 second? Okay. So to get the speed, what I want to do is I want to figure out the magnitude of the velocity at 1 second. Okay. And so what I would want to do is I would want to go ahead and plug in 1 here. So I would have 6 minus 1, so that's going to be 5 I hat. And then I plug in 1 for time, and I have 16 j hat. Want the magnitude of that. So that's going to be square root of, what, 256 plus 25, so that's 281. Square root of 281 meters per second. Okay. What if I asked, what is the direction of travel? At t equals 0 seconds. All right. So remember, the direction of travel has to do with the direction of the velocity vector, okay? So I need to evaluate the velocity vector at time 0. So what if I plug in time 0? Okay. That's going to kill the t squared term here. So I would have minus I. Okay. And then if I plug in 0 for the j component, I get 0 times j. So the velocity at 0 is just minus I. All right? And so if I were to draw that vector, it goes to the left 1, and it doesn't go up at all. So it's in that direction. That's the direction of travel at 0 seconds. Okay? Lastly, I could ask, what is the magnitude of the acceleration at a certain time? So then you would do the Pythagorean theorem on that. So you know what? I'm not even going to bother with that because I think you guys get it. Even though I have no feedback from you guys, I can sense it that you understand. So this is CHL 910, period 5, part 2. All right, so last year we learned 3 really important equations, okay? Last year we learned 3 really important equations. They were called the kinematics equations, okay? And we're actually going to derive those equations in the last part of class today. This is going to use some calculus, so if you're taking calculus for the first time currently, this part is not going to make sense. And so I will ask you to go ahead and start on the quiz for today if you are just taking calculus for the first time. But I want you to stay on this YouTube live stream because I'm going to tell you when to go over to the Zoom room. Okay? So we're going to derive the kinematics equations. All right? And then on Monday, we're going to learn to do some really difficult kinematics equation problems. Okay? So, what are the kinematics equations? Well, the first thing we're going to do is we're going to talk about one-dimensional motion. So, when you have one-dimensional motion, the whole idea of having an I and a J is kind of irrelevant. Okay? Why? Why is that? It's because you're only moving along one direction, so you only need one of the components. Okay? And if you only have one component, you don't really need an I and a J. So when we're describing one-dimensional motion, we'll just have x of t without the i's or the j's, okay? Because it's just one-dimensional. And then in one dimension, the velocity is just dx dt. We don't have to take the derivative of the second j term. And the acceleration is dv dt. All right? So that's how it works in one-dimensional motion. Now, what if we have a situation where the acceleration is equal to a constant? Okay? Constant acceleration. This is sometimes called uniform acceleration. That means that dv dt equals the acceleration, which equals a constant. So what I'm going to do is I'm going to go ahead and integrate both sides with respect to time. Okay? I'm going to integrate both sides with respect to time. From time 0 to time final. Okay? Now, if we look at this integral on the left-hand side, the dt's cancel out, and we just get the integral with respect to velocity. And when the time is 0, the velocity is v initial, the initial velocity. And when the time is t final, the velocity is v final, the final velocity. So we can go ahead and, because the acceleration is a constant, we can move it out of the integral. Okay? So evaluating that first integral is going to give me a times t. All right? Because the acceleration is constant, I can factor it out. Doing the integral on the left-hand side, we get v final minus v initial. Okay? Which I can rearrange, and I get v of t equals v initial plus at. So this is one of our kinematics equations derived using calculus. All right? Now what we want to do is we want to go one step further. Okay? So now we're going to write v of t is equal to the derivative of the position. Okay? So what I want to do is I want to do the integral again. So I have dx dt equals v initial plus at. And I integrate both sides with respect to time. From 0 to t. All right, and this one will go from initial position to final position. All right. So doing the integral on the left-hand side, we would get dt's cancel out, and I just get x final minus x initial. And then on the right-hand side, integrating a constant is going to introduce just a factor of t. And integrating t gives us t squared over 2. So we have 1/2 AT squared. All right, which I can rearrange this equation, and I can write it as x of t equals x initial plus v initial t plus 1/2 AT squared. So we have another kinematics equation that we used last year. Okay? And then there was a third kinematics equation. All right? And the third kinematics equation is v squared minus v initial squared equals something. So let's work that equation out. So I'm going to write this v squared minus v initial squared as v plus v initial times v minus v initial. Okay. So what is v plus v initial? V plus v initial is going to be v plus v initial is going to be 2v initial plus at. So adding v initial to that term would give another v initial here. And then v minus v initial is just at. Right? If I subtract v initial from both sides, I just get at. And then I do this multiplication. I just distribute. So we get 2a v naught t for that first multiplication. And then for the second one, I get a squared t squared. All right. Now I'm going to factor out 2a. And what's that going to leave behind? It's going to, if I factor out 2a from the first term, it's going to leave behind v naught t. And if I factor out 2a from the second term, it's going to leave behind 1/2 at squared. All right. And v initial t plus 1/2 at squared, that's just this kinematics equation right here. So that's going to give me delta x. All right. So what I've just done is I've just done a calculus-based derivation of the three kinematics equations. So that was just for your enjoyment. That wasn't. You have to know how to know the kinematics equations, but I just really enjoy, deriving them with calculus. I think it's kind of a fun application of calculus to physics. Okay, so I hope you enjoyed that. And that's my lesson for today. So we're going to jump over to the Zoom room, and I will meet you there in about 1 minute.